Now that we have our theoretical model built, it's time to see how we can take that theoretical model to the data. And this is where identification starts to come in. And also, one thing I should have mentioned in prior videos is that we should always be having the end in mind when we're doing these modeling exercises, which is to say, we should have some policy experiment in mind that comes at the very end of this process, but we should be working towards that policy experiment even from the very first when we're developing our theoretical model and thinking about how it can be taken to data. And that's to prevent any sort of mechanisms being baked into the model, which would limit its ability to be policy relevant. Now that we've got the theoretical model, we need to start taking it to data. And this is where we start to leverage our knowledge of statistics and econometrics. And as we're going through this process of taking the model to the data, we should be asking ourselves two types of questions. First are data questions, which is just to say, are the variables that our model has in it reliably measured in the data, if at all? If we don't have data on key variables in our model, then we're going to have a limited ability to actually identify the parameters associated with those variables. And then the second is specification questions. When we talk about specification, what we're talking about is what are the distributions of the error terms that are unobservable? Or what's the functional form of utility? Are we having something that's linear in parameters, that's additively separable with an error term? Are we measuring years of schooling in a continuous manner, or are we treating schooling as a binary, you got your college degree or not? Sometimes we have parameters that we have no hope of identifying, and in these cases, we might consider calibrating values for them, which is just to say, assigning a value to it and then checking later if that value makes sense given what other studies have found for similar parameter values and given what we know about the world in general. Now that we've kind of talked through this process, let's apply our theoretical model from the previous video to some actual data from the National Longitudinal Survey of Youth 1997 cohort. We've got some code here in Julia that reads in a CSV of data, and then we can look at what's in the data. There's 6,009 observations. That's the sample size. That's the number of people in our data. And we can see demographic characteristics about them. We can see whether they're employed or not as an adult, what wage they're earning, whether they received a college degree, how old they are, whether their parent went to college, how many children they have in their household, and this EFC variable is something approximating their ability to pay for college. Right here, we can start to see that we have the beginnings of some similarity between what we had in our theoretical model and what we have in our data. This EFC could be a proxy or could be a rough measurement of the cost of schooling. This number of children is exactly the variable K in our theoretical model from before. Parent college could be the Z variable, that's the family background variable. And then we have a 0, 1 for if they graduated college. That could be our S variable. And then we have their wage, which is the W in the log W formula. And then we have a binary variable for if they're employed as an adult. So that would be their second period choice. So right now it seems like we have a minimal set of variables to match with what we had in our theoretical model. Now that we've gone through this exercise looking at the data, we might also need to make some other assumptions to our theoretical model. So this is why we might want to be working backwards and thinking about what's in the data before we specify our model, because then that's going to otherwise create this additional work where we need to go back and revise our model. An example of this is with the years of schooling. Maybe in our theoretical model originally we had hoped that years of schooling could be continuous, but then when we look in the data, we only see a college diploma indicator, and so we're going to have to treat it as binary. Likewise, if we wanted potential experience to be continuous, we're going to need to walk that back and then simply assign potential experience to be age minus 22 if they're a college graduate, age minus 18 if they're not a college graduate. Then we need to make assumptions about the error terms. So maybe we assume that wages are log normally distributed, so that would mean that the epsilon is going to be normally distributed. And then maybe we assume that the choice epsilons or the error terms in the choice models are logistic, and that's going to make estimation a little more simple. And then we make some assumptions about linear in parameters and these other types of functional forms for the utility functions. And then once we've done this, we can we have sort of a new system of equations that is something we can take to the data. So this slide summarizes the assumptions that we've made based on the data that we have. We're going to assume that epsilon is normal, that eta k is logistic for k equal 1 to 2. We're going to assume that the schooling decision is a function of whether the parent went to college. That would be the z variable from our theoretical model. And EFC, which is the schooling cost variable, which is just some measure of ability to pay by the family. And then in the second period, we might assume that k is the number of kids, which is given what we had already seen in the data. That makes sense. And then maybe the expected log wage also enters the decision to work in the second period. So we have everything here that we could use to actually take our model to some data, because everything in here is something that's in the data, or it's a functional form assumption just from a statistical distribution. Everything that's on this slide we can use to build a statistical objective function, either a likelihood function that we're going to maximize, or a moment-based function or a distance function that we're going to try to minimize. So this is how we implement practical specification issues in the realm of our statistical model to try and make sure that we are making progress down this path towards creating meaningful empirical results that can be used for real-world policy.